Hey guys, we are back for round 2 this week. I know you guys are loving it because it's not like in class, right? That you just go through the whole experience and then it's over. But now you can rewind this and watch it day after day after day. So I'm sure that's exactly what's happening at home. I want to talk about enthalpy today. Enthalpy can be thought of as it's a concept that has to do with the measure of potential energy in a chemical reaction. And so that's very hard to measure in a chemical reaction. So what we're, as far as what the potential energy is, at the beginning when you have a system, what we actually pay more attention to and what we can measure is the change in enthalpy. Enthalpy is typically denoted by a capital H. So when we talk about the change in enthalpy, this is the energy change that accompanies a chemical or physical change. So, enthalpy is relevant in systems that aren't just chemical processes, but of course, for this class, we're going to be looking specifically at at how it applies to chemical reactions. And so, like I said, this triangle H, right, stands for change in enthalpy. That's what that means. All right. So make sure you understand that definition, and that's something that we can actually measure. And so let's think about potential energy for a moment. So when we have an exothermic reaction, we have all this potential energy at the beginning, and then because energy is released in this reaction, that energy is expended, and so the potential energy that's left at the end of the reaction is smaller than the potential energy we have at the beginning. And if you remember, whenever we were looking at change in temperature during the last chapter, we said change in temperature, we figured that number out. Should be obvious, common sense, that we figured out the change in temperature in a system when we look at the final temperature and we subtract from that what the starting temperature was. Well, if the final potential energy in a system is small, right, if it's a small number, and then we're trying to determine the change in energy, and so we have to subtract from that the potential energy at the beginning, which was a big number. If you subtract a big number from a small number, what are you going to get? You're going to get a negative number. All right? And so that's exactly what we find whenever we measure the change in H for an exothermic system, a system that starts off with a large amount of potential energy, and because a lot of energy is released, then we have a small amount of potential energy at the end. So we want to write that down and make sure we're aware of that we remember this, and we're going to use this over and over throughout this chapter, that change in H is negative for exothermic reactions. All right? And so it should be obvious to you that the opposite of that is true. Change in H is positive for endothermic reactions, right? And so make sure you know that. That's supposed to be a little star there. By the way, the typical units for change in H are usually not measured in joules, but kilojoules per mole when we're talking about chemical reactions. Okay? All right, so let's talk about enthalpy and bond energies. Enthalpy and bond energies, and then we'll do an example. Now that we understand what enthalpy represents, let's see if we can calculate it using something called bond energies. And so I want you to consider this equation. 2H2 plus O2 yields 2H2O. Now, if you'll remember, way back at the beginning of the year, whenever we began to look at the different types of chemical reactions, we said that this is a combustion reaction, right? You take some substance, you combine it with oxygen. That's what happens when we burn it. We combine it with oxygen in gas form, and then we have some output there of the combustion. So this is a reaction for the combustion of hydrogen. And the reason I wanted to point that out is because we already know if this is the combustion of something, then it's going to produce energy, right? It's going to release energy. In other words, this is going to be an exothermic reaction. We're going to feel the heat from the reaction. That's energy that's being produced. The light that we're going to see as this reaction takes place. This is a reaction that produces energy, okay? So we know going into this that this one here is going to be exothermic. Well, let's break down what's happening here on a chemical bond level. Let's go back to Lewis structures. If you remember those, with hydrogen you have two hydrogens that's bound together by a single bond, right? So for the 2H2O here, we've got two of these, right? And then for the O2, we've got oxygen with a double bond, all right? And we could, if we drew the valence electrons around there, we'd see how these paired up like that. And so these covalent bonds make sense here. And then for H2O, the Lewis structure looks like this. And we've got two of them on this side. So that's what the Lewis structures look like for both of those water molecules on that side. Now, understand what's got to happen here. These two bonds between the H's are going to have to break, right? Because we don't have those bonds over here anywhere. Same goes for this double bond with the oxygen atoms. This is going to have to break apart. And then bonds are going to reform over here as the hydrogen and the oxygen atoms are bound together. And so from an energy standpoint, what happens here is that the breaking of the bonds absorbs energy. In other words, it's going to take energy. It's going to take energy in order to break these bonds, and then energy is going to be released as new bonds are formed over here. All right. So we've actually got now kind of a mathematical equation that we can write down, and that equation says that the change in H is going to be equal to the energy. We'll put these in parentheses. Energy to break bonds minus energy to form bonds, right? So if you take the energy required to break the bonds and you subtract from that the energy to form the bonds, that's going to give us our change in H. And so we need to define something here that we call bond energies. And bond energies are, let me do that singular. Bond energy, that's the energy required to break 1 mole, to break a mole. See my shirt today? Thank you, students, for my shirt. To break a mole of a given type of bond. And by the way, if you've been noticing my chemistry shirts and you're thinking, man, Mr. Walker spends a lot of money on chemistry shirts, I have not bought one chemistry shirt. I just have loving students, and you guys have provided these wonderful shirts for me. So I can basically wear one like every day of the week. Not quite yet, but I'm getting close, all right? So anyway, what is bond energy? Bond energy is the energy required to break a mole of a given type of bond. And if we know the bond energy for given bonds, then we can do this calculation here. So the nice thing is that we actually already, these measurements have already been made for us. And if you go to page 420 in the book, you're going to see a table there of bond energies. And so you'll see the energy in kilojoules per mole for the various bonds. Like at the top left, you've got two hydrogens connected together with a single bond. And so the energy required either to form that bond or to break that bond is going to be 436 kilojoules per mole, right? So if we have a table of bond energies, then we can do this calculation if we know what the bonds are in our chemical reaction, all right? So just one thing I want you to note in that table there, and that is you'll notice that the numbers are much higher down at the bottom where you've got highlighted values in yellow. Those numbers are much higher than the numbers at the top, and you'll notice the ones at the bottom, those are double bonds and triple bonds. So I just wanted you to notice that it takes more energy to break a double bond, and it takes even more energy to break triple bonds. And we said when we learned about these types of bonds that that triple was the strongest, right? So if you remember all of that, that should make sense to you that those numbers would get higher, okay? One other thing I want you to note is that HC, if you have this bond here, that's the same as CH, all right? So the order of the elements don't matter in these bonds, so both of those there would be 410 based on the table, kilojoules per mole, all right? So knowing that, let's do our first example. That's going to be example 14.1 on page 421. And just write this down. There's a little formula here. Change in H is the energy to break minus the energy to make. So to break the bonds, the energy to break the bonds minus the energy to make bonds, okay? So let's do this problem here is actually asking us for the bond, what the change in H is for the combustion of hydrogen, the example we just had a moment ago, 2H2O, all right? And so the question says, what is the change in H, right? I should have left all this stuff up on the board. So like we said, H plus H plus a double bonded two O's is going to equal O plus HO. All right? So let's think about what we've got on each side. Basically here we have two moles, right? 2 moles of hydrogen single bonds plus 1 mole of oxygen double bonded, right? And that's going to give us a total of 2 moles of H2O, but as far as the number of bonds go, we've got a total of 4 moles of this OH single bond, okay? All right, so now we can look at our chart and we can plug those numbers in to see what we've got. So for the H single bonds, that's 436. Whoops, forgot my units. 436 kilojoules per mole. See, that's why we've got moles in the front here. That's going to cancel out. Plus 1 mole of oxygen double bond. That's going to be 498 kilojoules per mole. And then on this side of the equation, we're going to have 4 moles times HO is 460 kilojoules per mole, right? So based on our definition here, change in H then is going to be equal to the energy required to break the bonds, the amount on this side. So it's going to be, that's 2 times 436, plus 498 minus the energy to make, which is this value over here, 4 times 460. And as we can see from the units here cancel out the moles, we're going to be left with a unit of kilojoules, right? Because all these mole values cancel out. So that total number there is going to be negative 470 kilojoules. And like we said before, we know combustion is an exothermic reaction, and so we expect the change in H to be negative, right? So we got exactly what we expected. So don't forget that. Negative change in H means we're dealing with an exothermic reaction. Positive change in H means that we have an endothermic reaction. All right, so that's it for enthalpy and bond energies. We'll look next at a more accurate way to determine the change in enthalpy. See you shortly.